Okay, I guess we don't have any questions. Okay, today we'll continue from where we ended. Remember, I gave you guys 3 objectives last week. Oh, on Monday. I'm sorry, on Monday, but we only managed to do just one explaining. We only managed to do the explanation of concepts of average and marginal revenue and cost. So today we'll start from using differentiation to optimize economic functions. And then if we still have time, we'll use differentiation to determine the intercepts of point elasticity. And then we'll move to integration if we still have time. And another thing, remember, we don't have classes next week and the following week. So our next class will be on the 26th of this month. Is my screen still showing?
Yes.
All right, thank you. Okay, today we'll start from optimization of economic function. Okay, if you see that I'm fast, please feel free to stop me immediately or to let me know. Just unmute your mic and talk if you have a question. I don't mind. Okay, guys, in the last chapter you had with Prof, which was chapter 5, you found the turning point, right? He did the differentiation, which is chapter 5. You find the turning points for a nonlinear functions, right? And you find the first derivative is equal to 0 in a turning point. Okay. What I'm saying is, so in that chapter, to find the turning point, you differentiated a function. Let's say you want to find a turning point of a function f. Then you differentiated that function f and you equate to 0. Then those points that you will find when you equate the derivative to 0, we call those points the turning points. And to find the nature of those points, you differentiated twice, meaning you find the second derivative. And from the second derivative, okay, let's say our function was f at x, right? To find the points where the graph has a turning point, you differentiated once and you equate to 0. And then you solve for x. And those x that you will find here, we call those the turning point of f at x, right? And then to find the nature of this turning point, you differentiated f at x twice, meaning you find the second derivative of f at x. And we said if the second derivative of x is greater than 0, then the point x is a minimum point, right? Minimum point. And if the second derivative of x is less than 0, then we said x is a maximum point. Okay. Guys, if there is someone in the loop, please admit them because I won't be able to see them since I'm sharing my screen. Okay, this is what we did. This is what we did in chapter 5. Now we want to apply this in the economic functions, like in the total revenue, in the total cost, in the profits. Okay, and we call that, okay, if we apply the process of applying these to the economic function is called the optimization, right? Although optimization differs for any company, but the objective of optimization is to obtain a technique or a condition under which the marginal revenue is equal to the marginal cost. Yeah? So the optimization is done differently per company, but what is common in everything is that the goal is to find the condition whereby the marginal cost is equal to the marginal revenue. Okay, this is the point for doing optimization. Okay, the reason we have to find the condition whereby the marginal cost is equal to the marginal revenue is because at this level the profit is X maximum. So the profit is X maximum in this level, right? Whereby the marginal cost is equal to the marginal revenue. So my point is the reason we are doing optimization is because we want to maximize the profits. Ne? Remember, the marginal cost is the change in total cost resulting from 1 unit change in output, and the marginal revenue is the change in total revenue resulting from 1 unit in a sale, right? Okay, let's try and apply these in one of the example, which is the economic example. Okay, let's say, for example, let's say we are given a demand and a total cost is, okay, this is our demand. And we are given a total cost too is okay. Let's say we are given these two, the demand and the total cost. And the question is determine the price and quantity for which the profit is maximized using the differentiation as well as the marginal cost. Okay, remember we said the profit is at maximum if the marginal cost is equal to the marginal revenue. Right. Now we are asked to determine P, which is, okay, we are asked to determine the price and the quantity. Okay, just P and Q, at which the profit is at maximum. Okay. We said the turning point, okay, from chapter 5, we said the turning points are the maximum points, right? And to find the turning point, we differentiate that function we want to find the turning point for. Okay, but in this side, they said we should determine the price and quantity for which the profit is at maximum, and using differentiation as well as the marginal revenue and the marginal cost. Okay, we are asked to use the marginal revenue, marginal cost, as well as the differentiation to find the price and quantity where the profit is at maximum. Okay. What we know is the marginal revenue is equal to the derivative. Okay, we find the marginal revenue by differentiating the total revenue, right? And we find the marginal cost by differentiating the total cost, right? But here we are given the total cost and the demand function, right? So this means we only have this, which is the total cost. We don't know the total revenue, but we know that the total revenue is equal to the demand function times the quantity, right? Which is just PQ, right? And we know that P, which is the demand in this case, is equal to this function. So in the formula for finding the total revenue, we can just substitute P with that function, right? So this means our total revenue is 5,504 minus 0.8 Q times Q, which gives 5,504 Q minus 0.8 Q squared, right? So this means now we have the total revenue and we do have the total cost, meaning we can now find the marginal revenue and the marginal cost because they said we should use that, right? So we said the marginal revenue is the derivative of the total revenue with respect to Q, right? So this means our marginal revenue now, okay, the derivative with respect to Q, the derivative of 5,504 Q minus 0.8 Q squared, right? If you differentiate 5,504 Q, what do we get? Anyone? Guys, are you still there?
Yes, ma'am.
Right. If you differentiate 5,504 Q with respect to Q, what do we get? We get 5,504, right? Guys, you did differentiation with Prof. And if you differentiate minus 0.8 Q squared, what do we get?
I think it should be 1.6 Q.
Don't forget this minus, ne?
Sorry, the minus, yes.
1.6 Q. So we have the marginal revenue as 5,504 minus 1.6 Q. And we also need the marginal cost, right? And we said the marginal cost is equal to the derivative of a total cost with respect to Q. And we know that the total cost is 608,580 plus 120 Q. So what would be our marginal cost in this case? We just have to differentiate this function with respect to Q. If we do that, what do we get?
And see the number properly. So what's that number? 60?
608580 plus 120Q.
120.
Okay, we have 120. So we have our marginal revenue as this, and we have our marginal cost as this, right? Remember, the question in the question we were asked to find the price and the quantity for which the profit is at maximum, right? And we know that when P is at maximum, P is at maximum when the marginal revenue is equal to the marginal cost, right? And we said our marginal revenue is 5504 minus 1,6. So from this condition, where there is marginal revenue, can substitute marginal revenue with each function, right? And where there is marginal cost, we substitute marginal cost with each function, which is just 120 in this case. So now we have 5504 minus 1,6Q is equal to 120, right? And remember, our aim is to find P and Q, the price and the quantity, right?
Sorry, ma'am.
Yes.
How to get the 120? Can you please clarify for me, please?
Yeah, we obtained 120 here. We were differentiating this function. You still
Using the
remember?
calculator.
Pardon?
Using the calculator.
No, we don't use the calculator in differentiation. Okay, let me doing examples somewhere else. Okay. Remember the differentiation. We said if we're given a function f at x is equal to ax to the power n, and we are asked to differentiate this function, meaning we want to find f prime at x, right? And f prime at x would be, you take this power, you multiply it by this coefficient, and you'll have a n x to the power. Then you add, you subtract 1 here from the power. So n minus 1, right? And this would be the derivative of this function. And this is what we're doing here. Now, okay, here we have a second. Right. Okay. Yeah. Is my screen still showing?
Yes.
Okay, thank you. Here we have this function, right? Meaning we have, it's like we have f at x is equal to 608580 plus 120q, right? 120x, because now we said it's f at x. Okay, but then we can use f at q and we write q here. It's fine. Okay. Another thing that you should remember is x to the power 0 is equal to 1, right? From the laws of exponent. And if this is the case, this means you can write this function f at q as in 0.80850 q to the power 0, right? Plus 120 q, right? Do we agree with this? Yes, no?
Yes.
Okay. Now our function is like this, right? And going back to our differentiation, we said if you have f at x is equal to a, we said if we have f at x is equal to ax to the power n, then the derivative of this will take x and n and multiply by n, and then it should be an times x to the power n. Then you subtract 1 here. So now the derivative of f at x is equal to ax to the power n would be an x to the power n minus 1, right? Okay, here f at x is equal to a x to the power n. Now the derivative of f at x would be an x to the power n minus 1, right? Okay, let's take this part, only this part for now. Let's say our f at, okay, we'll take this part and compare this part to this one, right? If we look at, okay, if we compare this and this, it's like our a is equal to 808580, right? And our n is 0. Our n is this 0. We have n is equal to 0, and we have x is equal to q. X is equal to q, right? Now, I want us to take these and substitute them here. And if we do that, that means we'll get f at q, f prime. Okay, remember where there is x, we put q. Where there is n, we put 0. Where there is a, we put this, right? So this means we'll have f prime at q is equal to, we have a, and a is this. We have 0, 8, okay. This is 6, 0, 8, 5, 8, 0, right? Times, we said our n is 0, right? So this means it's times 0, right? And we have x, and we said our x is q. So we have q, and our q is q to the power n minus 1, and our n is 0, remember. So it's 0 to the power minus 1, right? And if you simplify this, you'll have this times 0. Any number multiplied by 0 is 0, right? So this means we have this times this, which give us 0. 0 times this is 0, right? So this means if we differentiate this function, we'll get 0, right? And now we are left with 120Q. Okay, we have F at Q is equal to 120Q, right? Again, I want us to compare this with this function. And if we compare this with this function, okay, first, before we compare this with this function, if we have x is the same thing as x to the power 1, right? Because if we have, let's say we have 5 is the same thing as 5 to the power 1, right? Do we agree with that?
Yes.
Yes.
Now we have 120Q. 120Q is the same thing as 120Q to the power 1, right? So this means our F at Q is 120Q to the power 1. And if we compare this function with this means our A now is 120 and our N is 1, right? Is 1, and our Q is X, Again, I want us to take this and substitute them here. Our X is equal to Q, our A is 120, and our N is 1. And if we do that, we'll get F prime at Q is equal to, we have A as 120, so it's 120 times N is 1, so it's 120 times 1. Then 120, it's ANX, our X is Q, so times Q to the power N, our N is 1, right? To the power N minus 1, right? So this means we have F prime of Q as 120 times 1 is 120, right?
Yes.
120Q to the power 1 minus 1 is 0, right? And we said X to the power 0 is 1, right? So this means Q to the power 0 is also 1, right? So where there is Q to the power 0, can substitute Q to the power 0 by 1, right? So this means this function becomes 120 times 1, which is just 120. And that's how we found that this 120.
Okay, thanks. Now I understand.
Oh, all right. Thank you. Where was I? All right. Now, after finding the marginal revenue and the marginal cost, we equate them, because the question was determine the price and the quantity where the profit is at maximum. And we said the profit is at maximum when the marginal revenue is equal to the marginal cost, right? Okay. If we equate these two, you see we only have one unknown, which is Q in this case. So we can use this condition to solve for Q. And if we solve, to solve for Q, right, we need to make Q the subject of the formula. And to do that, we'll have 1,6 Q is equal to, we transpose to the other side. So we have 1,6 Q is equal to 5504 minus 120, right? Because we transpose, what I did, I took this to this side and I took this to this side. And if you transpose to the other side, remember the sign changes. So that's why I have 1,6 Q instead of minus 1,6. And that's why I have now I have 120 instead of, now I have minus 120 instead of 120. So this is what we have. And 1,6 Q would be, okay, we have 5504 minus 120. What is that?
It's 5,384.
We have 1,6 Q is equal to this. We don't want 1,6 Q. So to cancel out 1,6, we need to divide by it on both sides. So that will be left with Q alone. Remember, we want the quantity, not 1,6 times the quantity. So now we'll be left with Q.
It's 5384, not 5388.
Oh, 5384. Thank you. Then we have 5384 divided by 1,6. What do we get?
It's 3365.
See, this Q, which is the quantity, we obtained it when the profit was at maximum. Because when the profit is at maximum, marginal revenue is equal to marginal cost, right? So this means we have the quantity at maximum now. Okay, remember, initially we were given the demand function, and in the demand function we do have the price, and now we do have the quantity at maximum. So what we have to do is to take that quantity at maximum, which is 3365, and substitute it here in the demand function. And if we do that, we'll get the price at maximum, right? So this means we'll say price is equal to 5504 minus 0,8. Okay, remember this was the demand function. Here we have Q. This was the demand function, we were given this. And now we have this quantity at maximum. So you just have to take this and substitute it here. And if we do this, we'll get the price at maximum. So we'll say P is equal to 5504 minus 0,8 times 3365. And that would be our price at maximum, what we're asked to find. Please check this one for me.
It's 3821,50.
We have 5504 minus 0,8 times 3365.
I'm getting 2812.00.
0.00. Okay.
Yes.
Do we all agree with this one?
Yes, we do. I'm also getting the same.
Okay. And this would be our final answer. This one and this one. Are we still all together? Do we have any questions? Yes, no?
Still together.
Okay, let's move on.
Yes.
Let's try and do another example. let's say again, we are given a demand function as P is equal to 200 minus 3Q, whereby this P represent the price per unit and this Q represent the number of units produced and sold. Okay. We are trying to apply the process of optimization here. Remember, we said in this section, we are applying optimization in the total revenue, total cost, and the profits, right? Let's say now we are given this and we are asked to apply this is in any of the functions. Let's say, for example, in the total revenue. Okay, if we are given the demand function and we are asked to maximize the total revenue, né? What is the first thing that we need to do?
We need to get the total revenue.
Yes. Okay, and we know that total revenue is equal to the price per unit times the number of units, right? Which is just P times Q. And we know that P, which is the price, is given by this function, by this demand function. So our total revenue would be 200 minus 3Q times Q, right? Which if we multiply, if we simplify this out, we'll get 200Q minus 3Q squared. This is our total revenue. Okay. Then what is the next step that we need to do?
We're missing the total cost here.
Remember here I said let's just maximize the total revenue only.
Okay.
We can do the total cost after if we can do it. But for now, let's just maximize, let's try and maximize the total revenue. We want to find, let's say we want to find how many units can be sold when the
Yes.
total revenue is at maximum. Remember, at maximum, at maximum, the function is at maximum on the turning points, right? And to find the turning point, we need to derive to find the first derivative, right? And the first derivative of the total revenue is the marginal revenue, right? So this means for us to get for us to get to know the revenue at maximum, we first need to find the marginal revenue, because the marginal revenue is the derivative of the total revenue, right? And we know the total revenue. What do we get if we differentiate our total revenue? Anyone?
Not 200 minus 6Q, no?
Yes. Do we all agree? Okay. Now we have the total. We have the total revenue and the marginal revenue, and the marginal revenue is the derivative of the total revenue, right? Okay, meaning we have the derivative, and our aim was to find the turning points, right? And remember, to get the turning point, you equate the first derivative to 0, right? So this means our total revenue has a turning point whereby the marginal revenue is equal to 0, right? Now you just want to find the points where the total revenue has the turning points. And to do that, we have to differentiate the total revenue and we equate it to 0. And those points that we will find, those Q points that you will find there, will say those are the turning points for total revenue, right? Remember, in chapter 5 with Prof, you were given f at x, right? And we also find the turning points of f at x. To do that, you say you find the derivative of f at x and you equate to 0. And those x points that you will get when you differentiate and you equate to 0, you call them the turning points of f, right? Again, we are doing the same thing here. We have the total revenue, which is this, and we differentiate, and we said the derivative of the total revenue is the marginal revenue, right? Which is this in this case. Now we want to find this x star, which is at the turning point of f at x, meaning we want to find the turning point of the total revenue. And the f prime here, if we compare this with the total revenue, the f prime here is the marginal revenue, because we said if we differentiate the marginal revenue, the total revenue we get the marginal revenue, right? And we said to get the turning points of f, we have to equate f prime to 0. In this case, we equate the marginal revenue to 0 to get the turning points for total revenue, right? Are we all still together?
Yes.
Following, ma'am.
Right, thank you. So we equate the marginal revenue to 0, and this is our marginal revenue. If we equate that to 0, we'll have 200 minus 6Q is equal to 0. This means, okay, we have to solve for Q here. If we solve for Q, we'll have 6Q is equal to 200. We want Q only, not 6Q. So that means we have to divide by 6 on both sides. That means we have Q is equal to 33, right? And this means 33, Q is equal to 33 is the turning point for our total revenue, right? Now we want to find the nature of our turning point. Ne? Remember, the nature of the turning point tells us whether the turning point is the maximum point or the minimum point. And if we apply that here, that means the nature of this point, which is the turning point, will tell us whether the total revenue is at maximum or is at minimum. Okay, remember okay, the nature of the turning point, if f prime prime, which is the second derivative of x, if it's greater than 0, then that is x is the minimum point, right? And if second derivative of x is less than 0, then x is the maximum point, right? So this means we need to find the second derivative of the total revenue, and we substitute this q. Yeah? If the second derivative of this q is less than 0, that means the total revenue at this point, which is 33, if it's less than 0, then we'll say is at maximum. If the second derivative of the total revenue is greater than 0, then we'll say the total revenue at this point, which is 33, we'll say it's at is a minimum point. Okay, let's try and find the second derivative. We said the first derivative is equal to 200 minus 6q. To get the second derivative, we need to differentiate the first derivative, right? So this means the total revenue, the second derivative of the total revenue is the derivative of the marginal revenue. Remember, the marginal revenue is the first derivative, right? With respect to Q, which means we differentiate 200 minus 6Q with respect to Q. And if we do that, what do we get? We differentiate 200 minus 6Q with respect to Q.
6.
Minus 6.
Minus 6. Right? Then we have the second derivative as minus 6. You see, minus 6 is less than 0, right? So this means the second derivative, the total revenue, the second derivative of Q, where Q is 33, is minus 6 is less than 0. That means, this means since it's less than 0, the turning point is at maximum, right? So this means we have, if we sell 33 units, then we'll get a revenue which is at maximum. We'll have a maximum revenue, and then we need to find how much would be our total revenue if we sell 33 units. Now we know that our units would be 33 at maximum. Now we want to find how much would be our total revenue at maximum. We know it's at maximum. That is the nature of the total revenue. We just want to find the amount now. Yeah? And okay. Remember, we did find the function for total revenue. We said the total revenue is 200Q minus 3Q squared. Okay, we have total revenue as 200Q minus 3Q squared. We have Q, we just have to substitute here. So this means our total revenue would be Q times 33 minus 3 times 33 squared. What do we get? What would be our maximum total revenue? Anyone?
Okay, 3,333. Was doesn't sound right, but
Do we all agree with this?
Yes.
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 Do we have questions? Can we move on?
just one question from my side. In terms of maybe an assignment or an exam, how will this question specifically, come across? How will they ask the question? Sometimes I think that's where I get lost, just the wording.
It's either determine the maximum total revenue or quantity that can be sold at maximum total revenue, or they'll just say maximize the total revenue. Or you will be given Q, which is the quantity, and they will ask you if with according to that, or when will they sell that quantity? Will it be at maximum or minimum? Or again, they will ask you about the total cost, but you do the same thing. You'll follow the same steps.
Okay.
Or maybe maximize the profits. If they ask you to maximize the profits, you'll find the total revenue and you'll find the total cost. Remember, the profit is total revenue minus total cost. Then after doing that, after finding the function for your profit, you'll then differentiate to find the first derivative, and that quantity after differentiating, you'll equate to 0 and you'll find the turning points, right? That would be the quantity that you'll sell at maximum or minimum. Then you'll do the second derivative of that profit function to check whether it's at maximum or minimum.
Thank you.
All right, thank you. Okay, can we move on? Please do. We have I think 5 questions, five examples there on the study guides. Please make sure you do them. I know I only did one. Please make sure you do all of them. Okay, guys, let's move on to elasticity of demand. We'll do them for nonlinear demand function. Nonlinear demand function. Okay, in chapter 2, right, you were introduced to the concept of elasticity, but you only did a concept of elasticity for linear demand function, right? Please do go back to that section just to revise, just to refresh your mind for this concept of elasticity, because you other conditions are the same and the formulas and everything. Yeah. Okay, the elasticity of demand sometimes is called the demand elasticity. Okay, that's just the same thing. Okay, the elasticity of demand is just a measure of how the demand responses to the change in price or income, right? This chapter, the elasticity of demand, it is important to companies because it influences the price the company will charge for their profits or service, products or service, right? And another thing, if a business knows or a company knows the price or how to find the price elasticity, it will help them develop a strategy to maximize profits or to reduce the risk. Okay, suppose you are given a demand function as P A minus BQ, right? Suppose you are given a demand function as in this, where A and B are just a constant. Okay, the point elasticity of demand for linear function would be defined using this formula. We use this formula to define the point of elasticity for linear, changing in P over changing Q, changing P over changing P times P over Q, which is the same thing as minus 1 over B times P over Q. Okay, if we are given this as the demand function, then for linear functions, you will use this formula to find the elasticity of demand in linear. Okay, for nonlinear, which is what we are doing today, we'll use derivative so that the elasticity of demand will be the derivative of Q over the derivative of with respect to P times P over Q. All right. You see, this depends on, okay, these derivatives depends on what you are given as your demand function. Yeah? Sometimes you'll have to find the derivative of P with respect to Q. Sometimes you'll have to find the derivative of Q with respect to P. It's depend on the formats of your equation, right? If the demand of the function is given in terms of P, is given in P, where P is the function of Q, then in that case, you'll have to find the derivative of P with respect to Q. But before you substitute on this formula, remember I said for nonlinear, this is the formula we'll use for elasticity, right? So before you substitute it here, you need to invert this. You need to find the inverse of this. And the inverse of this would be, okay, we want to find this, but we have this. So the inverse of this, which is dq over dp, will be equal to 1 over dp over dq. And then after finding this, you can just substitute it here, and you are free to use this formula. Okay, again, those conditions for elasticity still applies here. That's if the absolute value of the elasticity demand is greater than 1 at a certain price, then the demand at that price is elastic. Ne? If the elasticity of demand is greater than 1, then the demand is elastic. At that given price, meaning if the price increases by 1%, then the demand increases by 1%. And again, this still applies if the elasticity of demand is less than 1 at a given price, then this means the demand is inelastic at that given price. Meaning, if the price increases by 1%, then the demand decreases by 1%. Nah? And we have the absolute value of elasticity. If this is equal to 1, then we have uncertainty. It's either the price. Okay, this is when the price increases by 1 and the demand decreases by 1. Yeah? Okay, so these three conditions still applies even for non-linear equations. Okay, let's just try and do one example. Okay, let's say we are given a demand function as P is equal to 100 minus Q squared. Yeah? If this is the case, if we are given a demand function as in like this means we can find the derivative of P with respect to Q. The derivative of P with okay, it's like we are differentiating this function with respect to Q. If we do that, we'll get minus 2Q, right? So we have the demand function given given as a function of Q. And if that's the case, that means we can find the derivative of this function with respect to Q as minus 2Q, right? Yeah, but we said our formula for nonlinear elasticity of demand is the derivative of Q with respect to P times P over Q, right? We said is this, and from this equation, this is what we obtained, the derivative of P with respect to Q. Now we can, okay, to obtain this, we need to find the inverse of it, right? And we said dq over dp is equal to 1 over dp over dq, right? This means we have 1 over, this is just minus 2q, right? We have 1 over minus 2q. Since we now have this, we can just take this and substitute back to this equation, right? So that our elasticity of demand would be minus 1 over 2q times P over Q, right? And if we simplify this, this means we have minus P over 2Q squared, right? But we are given the demand function as in 100 minus Q squared. We have a demand function P is equal to 100 minus Q squared, right? Like always or all the time, you need to substitute or in the demand, in the elasticity of demand function, you need to get rid of that the demand, the quantity. Meaning, since we are given this, we need to get rid of the quantity here. Ne? So this means we can solve. You can solve for this here. And then you'll substitute this back to this, because I remember I said all the time, just make sure you get rid of the quantity and your elasticity of demand. Okay. We have P is equal to 100 minus Q squared. And you want to solve for Q in this case. Then, and if you do that, you'll have Q squared is equal to 100 minus P, right? But we want to find, oh yeah, in this case, we just want Q squared because we have Q squared. If we had Q here, then we would have added a square root to get rid of the square. So we would have Q is equal to the square root of 100 minus P, right? But this is just Q squared. And okay, now let's take this and substitute back here to have the elasticity of demand as minus P over 2 times 100 minus P. Now this is our elasticity of demand for that function. You can give yourself any price, because in this question we're not given any price. Let's say what will be the elasticity of demand if, say, if the price is 50 Rand. Né? If we are asked to find an elasticity of demand at this price, you just have to take this and substitute back here. And if we do that, that means our elasticity of demand would be minus 50 over 2 times 100 minus 50. This is minus 50 over 100, which is minus 0.5, right? Then we go back to our conditions. Our elasticity of the then we go back to our conditions, right? We said if the elasticity of demand is less than 1, that means the demand is inelastic, right? So this means if the price increases by 1%, then the demand will decrease by 1%. Are we still all together? Do we have questions? Pardon? Was that a question?
Okay, my question is, when it comes to the final amount, right? So we do the same thing, just like on chapter 2. For example, we ignore the sign and we just look at the value.
Yes.
Okay.
Do we have any more questions? Okay, I guess we don't have questions. Please let's move on to another chapter, which is integration. Theory, or just the theory of integration. Okay, guys, here, after this class, you have to know how to explain the integration as the concepts of the reverse of differentiation, that chapter you did in chapter 5. And we'll only do just one rule today because we don't have time. So after this video, you need to know how to explain the concept of integration as the reverse process of differentiation, and you need to know how to apply the power rule in integration, because we'll do only the power rule today. But in our next class, we'll do all the rules, and then we'll apply the integration, the theory of integration in our equations again, like in the total revenue, marginal revenue, profit. Yeah? We do the rules first, then we apply them. So for now, we'll do the theory of integration, which is the rule. And then later, we'll do the application of integration. Okay. Yeah, as I said, integration is the reverse process of differentiation. Yeah? Which is the reverse of differentiation. Okay, again, yeah, in maths, we have operators which are the reverse process of each other. Like if you like the addition is the reverse process of subtraction, right? And the multiplication is the reverse of division. If like you were subtracting and you want to go back to that same amount, you need to add what you subtracted before, right? And if you multiplied something and you want to go back to its initial state, you need to divide, because division is the reverse process of multiplication, right? Okay, this is similar case for integration and differentiation. Like to integrate, it's the reverse process of differentiation. Okay, this means if you have, like, say, f at x is equal to, let's say, f at x is equal to 4, right? And remember, if you differentiate this, you'll get f prime at x is equal to 4x cubed, right? We are given f,
Yes.
f at x, then you differentiate, you get this, right? Now, when you integrate, that means if you integrate these results, you should go back to the initial function, right? Like if, okay, we use this sign to show that we are integrating. As soon as you see this sign, just know we are dealing with integration there. Okay. We said if we differentiate this function, we get this function. Ne? Then to go back to here, you need to integrate this to go back to this, right? This is equal to f prime, right? So this means we're integrating f prime at x with respect to dx. This stands for with respect to what variable, right? We're integrating f prime at x with respect to x. That's why we have dx. And this sign is just the integration sign. Okay. Our f prime at x is 4x cubed, right? So we have the integral of 4x cubed dx, right? Because what we did here, instead of f prime, we substitute f prime because we said f prime is equal to this in this case, right? Then remember, I said if you integrate what you okay, if you integrate this, you should go back to this. Ne? So this means the answer here would be x to the power 4, right? Which is the same thing as f at x. This, we said this is our f at x, right? So this means we have something like this. We have fx, we have f prime at x. Ne? From here to here, we differentiate. Ne? We call this process a differentiation. This means we differentiate fx with respect to x. Ne? We get this. Ne? Then we move from here. If we move from here to here, we call that an integration. Meaning we integrate. And we said this is how we integrate. We write an integral sign of this function that we are integrating with respect to the function that we are integrating with. Remember, in the derivative, this dx stands for we differentiate with respect to x. And here, this dx that we multiply with stands for we are differentiating with respect to x. Remember, if we divide, the reverse process of dividing is multiplying. Ne? That's why when we're dividing here and we want to reverse, we multiply now. Because we said the multiplication is the reverse process of differentiation. Okay, we have rules in integration like in differentiation, right? Okay, remember the first rule in differentiation was the power rule, right? So even here, we'll start with the power rule. Okay. The power rule. Okay, this is for integration. Okay. Let's say again, we are differentiating a function such that, let's say our function is f at x is equal to, okay, let me go back to the one that I was doing. F at x is equal to x to the power 4, right? Remember, by power rule of differentiation, these f at x would be, if we are asked to differentiate this, we'll get f prime at x. We are using the power rule for differentiation, right? F prime at x would be the derivative of x to the power 4 with respect to x would be, we'll have 4x to the power 4 minus 1, right? Remember, you take this, you multiply it by, you take it down, and then you subtract 1. You take the power, you multiply with it, and then you subtract 1 from the power. And this will give you 4x cubed, right? This is how you apply the power rule in differentiation. Now, we said the integration is the reverse process for differentiation, right? So this means the power rule for integration would be the reverse process of the differentiation. Okay. This means the operator to get this 4x cubed. Yeah, to get this 4x cubed would be the reverse of this, right? So we want to move from here to here, right? This means we need to add 1 here, because you see here we have we have 4, and here we have 3. To move from here to here, we need to add 1 here, right? So we add 1 to the exponent. We have 4 here, but we have 1. To move from here to here, that means we need to divide with this, right? So this means our power rule here would be f prime at x. Okay, we are integrating this, right? So this means the integral of f prime at x would be, okay, our f prime of x is 4x cubed dx, right? We said to move from here to here, we add 1 here, right? So this means we'll have x to the power 3 plus 1. Okay, we still have this 4, right? But we have 1 here and we have 4 here. That means to move from here to here, we need to divide with this 4 to get rid of this 4, right? So we divide by 4. Eh? And this will cancel out, and we'll have x to the power 3 plus 1, which is 4, right? Okay, let's try and do another example. Let's say
Sorry.
we have, yes?
Okay, sorry to disturb. I would like to know when is our next class, because I see now we are running out of time. I have someone who's waiting for me, so I want to know when is our next class.
It's on the 26th.
On the 26th.
Yes.
Okay, thanks.
All right. Okay, I was about to do another example now. Let's say you have your f at x as x to the power 10. Now, and okay, this means if you apply a power rule here for differentiation, you'll have f prime at x as the derivative of x to the power 10 with respect to x would be, you'll have 10 x to the power 9, right? Okay. Now we want to move from here to here, right? You see, our power here is 10 and our power here is 9. To move from here to here, this means we need to add 1 here, right? And here, our coefficient is 1 and our coefficient is 10. To get rid of this 10, we need to divide with it, so that will be left with 1, right? So this means the integral of f prime at x in this case would be the integral of 10x to the power 9 dx. Running out of battery. In this case would be, we said we need to add 1 from the power, right? And we divide with this 10. Né? So this means the integral of 10x to the power 9 would be x to the power 10, right? Are we still all together?
Yes, ma'am.
Now, we know that the derivative of any constant is 0, right? The derivative of any constant is 0. So this means it is possible that the function that we're differentiating has a constant. That means what we've been doing might be wrong. né? For example, let's say when we are given f at x is equal to x to the power 4 plus 5. The derivative of this would be 4x cubed, right? And let's say we are given f at x is equal to x to the power 4 plus 10. The derivative of this function again, f prime at x, would be 4x cubed, right? Again, let's say we are given f at x is equal to x to the power 4 minus 10. Again, the derivative of this function, f prime at x is equal to 4x cubed, right? Do you agree with this?
Yes, ma'am.
Yes. Yes, ma'am.
Okay, so this means what we can do in the integration, we just need to add a constant. It doesn't matter what is the value of the constant. It might be 0, it might be something else, but we just have to add the constant in the integration. Ne? So this means the results of our example, in our example we had we had something like this. We were integrating 4x cubed dx, and we said the derivative with the integral, if we integrate this, we get x cubed, right? So what I'm saying is just add a constant so that it would be correct. And again, we're integrating x to the power 10, ne? And we said the if we integrate this, we'll get x to the power 11 over 11, right? Now, I said you should add a constant so that this would be correct. Ne? So this means the general rule for power rule for integration would be, let's say we are integrating x to the power to the power n, then this will equal to x to the power n plus 1 over n plus 1 plus a constant. So this is the rule that we will use for power rule in integration. Remember, the power rule in differentiation is the derivative of x to the power n with respect to n is n x to the power n minus 1. Now, the reverse process of adding, of subtracting is adding. That's why we are adding. The reverse process of multiplying is dividing. Here you subtract, you multiply with n, then you subtract. Here you add first, then you divide, then you add a constant. Do we have questions?
No, ma'am.
Not on my side, ma'am.
Again, did you guys see the recording? Monday's class recording?
Yes, I did.
All right, thank you.